Welcome to Dr. Paul Jones's Fun with Lewis Structures. So this presentation will cover calculating formal charge and figuring out valid and significant resonance structures of a given Lewis structure. So I've started with a resonance form, one valid Lewis structure for crotonaldehyde. Crotonaldehyde is a pretty commonly encountered chemical in an organic chemistry lab. I've shown everything, all the atoms are labeled except carbons, which I'm using the line formalism for. So there's a carbon here, and a carbon there, and a carbon there. You can also see my Fun with Line Formalism presentation, also to be uploaded fairly soon. So, the way this will work, occasionally I'll ask you to pause and do an exercise. So hit pause on the player, and then work it. Actually draw on paper what you're trying to figure out, and then come back and watch the solution. Okay, so this is crotonaldehyde. I've shown all the atoms, all the lone pairs. There are missing formal charges. So go ahead and figure out what formal charges are present and then what the net overall charge is on the molecule. So go ahead and hit pause and do that. Okay, you're back. So first, carbon here with 4 covalent bonds shown. So bond to H, bond to carbon, 2 bonds to that carbon, 4 covalent bonds to a carbon. It's got a formal charge of 0. So no formal charge there. Likewise, four covalent bonds on that carbon, 0. The oxygen has 1 covalent bond and 3 lone pairs. So you should think hydroxide on that one. So this oxygen, 3 lone pairs, 1 covalent bond, looks like OH, which has a charge of -1. So you can also calculate that using the equation. 6 valence electrons minus 6 lone pair electrons minus half of 2 shared electrons. 6 minus 6 minus 1. This has a charge of -1, and so we can draw in a charge there. I'm going to check and see if this looks okay. Yeah, you should be able to read that. Okay, so the oxygen has a charge of -1. That leaves this carbon. I guess I've left out the hydrogens, haven't I? All the hydrogens have 1 bond. A hydrogen that has a covalent charge, or 1 covalent bond, has a formal charge of 0. Almost every hydrogen you encounter in this class will have a formal charge of 0. It will occasionally have a partial positive charge, maybe even a significant partial positive charge. Very rarely we'll encounter molecules that have a partial negative hydrogen. But hydrogen with 1 covalent bond, which it should always have, will have a formal charge of 0. Leaves this carbon to figure out. It's got 3 bonds to it. No lone pairs are shown. You would have to show the lone pair. So you should get to where you identify 3 covalent bonds to carbon with no lone pairs as being a +1 charge. But you can go through the equation. So 4 valence electrons minus half of 2, 4, 6 shared electrons, no lone pairs. This is going to equal +1. 4 minus 3. So there's a +1 charge there, which you indicate with a plus that's circled. Okay, so there you've got the formal charges. What's the net charge? +1 minus 1. Net charge of 0. Okay, I'm going to erase these equations, so if you want to write them down, I'll try to announce when I'm going to erase something. You can write them down quickly, or you can rewind. You know how video works. All right, so net charge of -1. Now the rules, I'm going to next ask you to draw a resonance form, another valid resonance form for crotonaldehyde. So if you want to pause, you can go ahead and do that. If you want a review of the rules, I'm going to put the rules up just now. So the first rule, connectivity doesn't change. All right, so this carbon is bonded to 2 hydrogens and another carbon. In any other resonance form, it has to be bonded to 2 hydrogens and that other carbon. Likewise, this hydrogen is always bonded to this carbon. In every other resonance form, that hydrogen will be bonded to that carbon. This oxygen is bonded to that carbon. In every other resonance form, it's bonded to that carbon. This oxygen is bonded to nothing else. In every other resonance form, there'll be nothing else bonded to that oxygen. Now, for all of these, the number of bonds and the charges can change. So the electrons are going to move around. In resonance forms, 2 different resonance forms are showing different ways to distribute electrons around a given molecular skeleton. Given that, charge and bonding can change, but connectivity can't. If connectivity changes, you've got a different molecule. A chemical reaction will have taken place. Okay, so the second rule, net charge doesn't change. All right, the net charge should be the same. +1, -1, every resonance form of crotonaldehyde has to have a net charge of 0. If the net charge changes, you've actually, again, done a chemical reaction. You've either added electrons or taken electrons away. It's a redox reaction. The third rule is that the Octet Rule applies. Okay, so I'll show you some examples here in a bit where, well, I'll actually show you an example with this one, okay? How about that? So these are the 3 rules you're going to have to follow. So go ahead and, if you haven't written these down or if you don't know them, go ahead and write these down. I'm about to erase. Okay, so you can pause. I'll give you a chance. Let me check. This is the first video I've shot. That's got a little glare on it. So my office is not a studio, so I apologize for the quality. Okay. So go ahead and hit pause and draw another resonance form for crotonaldehyde. When you come back, I'll put one up. Okay, you back? So you've probably seen in the book on Wiley Plus the curved arrow notation. We're going to do a lot of curved arrows in this class. I haven't really talked about it in class much. I've let you read it in the book, but I'll talk about it here. So in the curved arrow notation, a curved arrow, a double-barbed curved arrow, indicates the movement of 2 electrons. So again, judging resonance forms, we're looking at how the electrons move. So the arrows will give us a gauge for that. So we could, for instance, take two of the lone pair, one of the lone pairs, 2 of the electrons, use them to make a pi bond to the oxygen. So this oxygen will make a pi bond to this carbon. Okay, you can't stop there. Remember that the octet rule applies. This carbon has a bond to H, 2 bonds to this carbon, a sigma bond here, that's already 4 bonds. If I make a pi bond to it, that's 5 bonds, it's 10 electrons, it violates the octet rule. So pushing these electrons here means these pi electrons have to move somewhere else. They can move to make a pi bond here because this carbon, the positively charged carbon at the end of the chain, only has 3 bonds to it. It doesn't have a full octet in the original structure, right? So if it doesn't have a full octet, it can take 2 more electrons. So we can move this pi bond there. And now this gives us, the arrows tell us where the new bonds are. All right, 3 lone pairs, one of them becomes a pi bond, so there's 2 left. Got to draw the pi bond in. Now the pi bond moves to here. Connectivity is the same, right? This carbon has 2 hydrogens in both structures. This carbon has 1 hydrogen in both structures. This carbon has 1 hydrogen in both structures. The oxygen's bonded to that carbon. Pi bonding can change and charge can change, right? This oxygen's now neutral. This carbon is now neutral, so that's okay. Okay, so like I said, if a negatively charged element gives away, if a negatively charged atom gives away electrons, it becomes more positive. Strike that. If any atom gives electrons away, it becomes more positive. So a negatively charged atom that gives electrons away will become neutral. If an atom accepts electrons, right, this positively charged atom is accepting electrons. So if it's a positive atom accepts electrons, it would become neutral. Any atom that accepts electrons becomes more negative. So what is the net charge on this molecule? Net charge is 0. There are no charged atoms. 2 bonds to oxygen, 2 lone pairs, that's neutral. 4 bonds to carbon, 4 bonds to carbon, 4 bonds to carbon. Those are all neutral. So net charge is 0, net charge is 0, they're connected the same. All you've done is changed where the electrons are in the molecule. This is a valid resonance form of crotonaldehyde. So hit pause if you need to, and tell me which one of these structures is more stable, a more important resonance contributor to the overall structure. Okay, if you're back, Obviously the green structure here, the new resonance form I drew, all the atoms have a full octet, all the atoms are neutral, so it's a more important resonance contributor. This is a better structure than this one, where you have an atom that doesn't have a full octet, where you have charges separated. So again, resonance forms are two different ways of representing the same molecule. So two different ways of parsing out the electrons over a carbon skeleton. And the trick is, drawing Lewis structures doesn't quite get the molecular orbitals right. And so to get the molecular orbitals right, you have to sort of draw a bunch of these structures and then sort of, in your mind, make an average. And so it turns out that crotonaldehyde actually looks a lot like this. If you go in and measure bond lengths and angles, right? sp2, sp2, sp2 carbons are all trigonal planar, it's flat molecule. It really looks like this. The crotonaldehyde actually looks like this molecule I've drawn down here in green. But important chemistry of crotonaldehyde is demonstrated by this resonance form. When we start talking about Lewis acids and bases, this oxygen is a Lewis base, donates electrons because it's got significant partial negative charge. This carbon is a Lewis acid. It accepts electrons because it's got significant partial positive charge. So this resonance form explains a lot of the chemistry of crotonaldehyde. So go ahead and hit pause and draw me one more reasonable, pretty good Lewis structure for this molecule. Okay, you're back. So I'm going to do this now in red. I'm going to erase the green arrows here. I'm going to draw the next arrows in red. We could just move the pi bond, right? So if I just move the pi bond from between these two carbons to between these two carbons, the resonance form I get will be this. Negative charge on the oxygen, nothing happens there, right? Positive atom gets electrons, it becomes neutral. Neutral atom loses electrons, electrons are going away from it, it becomes positive. I'm going to see how that looks on the screen. Yeah, I'm going to say you can read that. So this is also a valid resonance form. Again, it's all connected the same, the net charge is the same, and just as the original structure explains a lot of the chemistry of crotonaldehyde, so does this. And in fact, anytime you have a carbonyl, so I'll circle that in blue, carbonyl is a carbon-oxygen double bond. And that always will have an important resonance contributor of any carbonyl will have negative charge on the oxygen, positive charge on the carbon. That will explain chemistry that we'll see more of see some at the end of this semester. We'll see a lot of it in organic too. But the oxygen in a carbonyl, Lewis base, the carbon is a Lewis acid. Nucleophile, electrophile, base acid. We'll talk a lot more about that, but that's a form that you should keep in mind. That's obviously better than, for instance, right? If you were to simply move the electrons, the pi electrons down to the carbon, we would now have a positive oxygen that doesn't have an octet, and a carbon that's got a full octet but a negative charge. So again, when you're judging these structures, you want, as much as possible, keep the negative charge on the electronegative elements. Carbon doesn't love having a positive charge and no full octet, but you're going to see a lot of that. We're going to talk about a lot of carbocation molecules in this class. All right, I'm about to erase all this. So if you want to hit pause and write it down, that would be a good thing. I'm going to show you a couple of common mistakes people will make in resonance forms. So go ahead and do that. Pause. Okay. So a really common error people will make is to violate the Octet Rule. And so for instance, you pretty quickly learn that you can move pi bonds around and you can move lone pairs around. Well, so people will say, okay, I'll just move this pi bond here. I'll move the pi bond between two carbons to between two oxygens and see how that works. Okay, so then if you follow that arrow, The arrow tells us we don't do anything to that carbon, so leave this the same. And we get a pi bond there. So if I take electrons away from a carbon that's neutral, it will become positive. If I put electrons toward an oxygen, so that's now a +2 charge. The net charge has to be 0, right? So I've got a +2. This oxygen needs to be -2. So calculate formal charge. 6 valence electrons minus 6 lone pair electrons, right? So these 3 lone pairs are all still there. Okay, then minus half of 4 shared electrons. 6 minus 6 is 0, minus half of 4, indeed, that's -2. All right, a lot of you are already saying, well, Dr. Jones told me that carbon, nitrogen, and oxygen should never be -2, and that's accurate. The other thing, there's one other problem. It's all connected the same, the net charge is the same. This is obviously not a good resonance structure, right? Positive charges next to each other, a -2 charge on an oxygen. That's not a good structure. It's actually a completely invalid structure. Why? So I'll give you a second if you haven't figured it out. Why is this not a valid structure at all? Okay, if you're back. The reason is how many electrons you've got here. Okay, carbon, you all know that carbon can only have 4 bonds. You probably don't know it in your gut yet, but you will by the end of the semester. Carbon can only have 4 bonds. The reason it can't have more bonds is if it has 5 bonds, that's 10 electrons. That violates the octet rule. Nitrogen can only have 4 bonds if it doesn't have a lone pair, because then that's 8 electrons. Nitrogen with 4 bonds and a lone pair would be 10 electrons. That violates the octet rule. This oxygen has 2, 4, 6, 8, 10. The octet rule is violated. That's not a valid structure. You'll never see a carbon double bond or an oxygen double bonded with 3 lone pairs. So you can't just move the pi bond to any atom. The atom you move the pi bond to has to be able to accommodate that charge. So if you're going to move the pi bond, if you're going to move a pi bond to a new atom, the atom you move it to must not have a full octet initially, or it needs to lose a bond. All right, I'm going to erase this and do another example. So go ahead and hit pause and write it down if you need to. Okay, so go ahead and if you're back, I've got here, I keep very paranoid about this camera, as you guys know from class. So calculate a formal charge and draw a resonance form. Go ahead, hit pause and do that. Okay, so 4 bonds to carbon. I didn't draw anything in there. That was a mistake on my part. All right, curse my name, hit pause again, and redraw a resonance form. All right, sorry about that. 4 bonds to carbon, 4 bonds to carbon, 4 bonds to carbon. All those carbons have a formal charge of 0. All the hydrogens have 1 covalent bond, net charge of 0. Nitrogen, no lone pairs, 4 bonds. You should think ammonium, NH4+. So this nitrogen should have a +1 charge. Again, you can calculate 5 valence electrons minus 1/2 of 8 shared is +1. So we can draw a plus there. Okay, so the net charge on this molecule is +1. So if you want to draw a Lewis structure, and you want to use this curved arrow, we can move pi electrons. If you haven't caught on yet, you can't break a sigma bond. You can never break a sigma bond because that changes connectivity. So all you can move are pi bonds and charges and lone pairs. Okay, so pluses, minuses, lone pairs, and pi bonds. Moreover, the pi bonds need to be adjacent. They need to be separated by 1 single bond so that you can, I can move electrons there and then move electrons there. So there is a pattern, and the book does a nice job of kind of illustrating the pattern. And we'll go into, when we talk about alkenes, we'll talk more about why that pattern is there. The molecular reason, the orbital reason, quantum mechanical reason that you have to have the charges separated by a single bond. For now, just pick that up. So let's draw a resonance structure. We can pop these two electrons up. That'll neutralize the nitrogen, right? I've got a positive nitrogen, move electrons to it. That neutralizes that nitrogen. But I'm taking electrons away from a neutral carbon. That should make that carbon positive. Right? The pi bond moving up will make a lone pair. Okay, and so this should be positive. You can calculate that. 4 minus half of 6. 4 minus 3 is plus 1. Plus 1. Net charge is the same. Connectivity is the same. Nobody's got a violated octet, so that's a valid resonance structure. Okay, the next one then, hit pause if you want. If you haven't drawn another one, hit pause and draw one. You can draw one more. You back? Move this pi bond to there. Again, electrons moving toward the carbon that's got a vacant p orbital, positive charge, no octet. You can make another bond there. That'll leave that carbon. Electrons go away from a neutral carbon. That carbon becomes positive. So there's another valid. That's another valid Lewis structure. Okay, I'm going to do a couple more. So go ahead and hit pause and write this down if you haven't already. Okay, are you back? This is our new molecule. It looks a lot like the first one, right? Except I've actually taken one carbon out. So instead of 3 carbons here, there's only 2. This lone pair now is separated from the pi bond by a single sigma bond. Again, that's pattern recognition. That lone pair then is going to have some resonance contribution to that double bond. I'm going to erase this top molecule. Okay. So, resonance structure for that. Are there formal charges? I've drawn, how about I put these H's in? So, calculate a formal charge here. All right, so again, all the H's have 1 bond. Formal charge is 0. The 2 carbons have 4 bonds. Formal charge is 0. Nitrogen, 3 bonds in a lone pair. Formal charge is 0. Think NH3, ammonia. So go ahead and draw one. Go ahead and draw one Lewis structure. Another resonance structure. Sorry. Okay, you're back. So the lone pair can make a pi bond. That's, if I make this pi bond between the carbon and nitrogen, that carbon can't have 5 bonds, and so this pi bond has to break. Okay, so you push those out there. There's nowhere else for them to go. Those electrons can't go out on the H or anything. So this would be oh, crap, sorry. Screwed that up. All right, if I'm pushing electrons to a neutral atom, I'm adding electrons to a neutral atom, it's going to get a lone pair and a negative charge. So add that up. 4 valence electrons minus 2 in the lone pair, minus a half of 6. 4 minus 2 minus 3 is minus 1. Minus 1 charge. A neutral nitrogen gives away electrons, it becomes positive. This is a valid resonance structure of the initial molecule. Net charge is 0, plus and minus. All the connectivity is the same, so it's a good resonance structure. And in fact, again, the first resonance structure, all the molecules have a full octet. They're all neutral. This is the best resonance form you can draw for this molecule. The molecule that's got two charged atoms is not as good. However, again, the chemistry of this molecule is explained in significant portion by this resonance form. And so a lot of times what we're going to encounter is a minor resonance contributor does a lot of work in explaining the chemistry of a molecule. And again, the reason for that is this molecule is not either one of these structures, it's sort of an average of the structure. And so this one actually plays a role. Okay, I'm going to illustrate another common mistake with nitrogen. So I'm going to, well, I'll go down this way as I do that. So bear with me as I erase here. Okay, so like I said, people want to just move the pi bonds around. So a pretty common thing for people to do would be to move the pi bond that way, right? I moved the pi bond in the first place and got a new pi bond, so why not do this? You can't just throw away lone pairs, so that lone pair has to be there. Electrons move away from a neutral atom, that atom becomes positive, and you can check that. 4 valence electrons minus half of 6 shared electrons is +1. Nitrogen, so 5 valence electrons minus 2 in the lone pair minus half of 6. 5 minus 2 is 3, minus 3. Wait. Half of 8. Gotta always check your work. This nitrogen has 1 lone pair, 2 electrons, 8 shared electrons. So 5 minus 2 minus half of 8 is -1. So that has a -1 charge. Net charge is 0. Connectivity is the same. So why isn't this a resonance form of the initial molecule? Take a minute, think about it. Okay, if you're back, the reason again is the octet rule. That nitrogen has a lone pair, 2 electrons, 4 covalent bonds. 4 times 2 is 8. That nitrogen has 10 electrons. That violates the octet rule. Nitrogen can't do that. So this is simply not a resonance form. And that's a really common mistake. All right, I'm going to erase one last example. This is a pretty long one. This is a pretty long video. They won't all be this long, but I'm going to do one. I'm not going to work this completely. So this is a